Good morning, everyone. So I'm Chengyu. So today I'm going to talk about our work on finding kernel reference counting bugs. This is joint work with Chinese Academy of Science, and unfortunately, the leading authors they can't travel, so I have to present. So we know there are because the kernel is written in C, so we don't have garbage collection, and we don't have this. All these fancy mitigations in C++ like smart pointers. So kernel memory management bugs are still quite common. And a lot of them, as discussed in the first paper you already listened to, have severe consequences like use of the free and double free. Okay, so the kernel already tries to basically mitigate these problems by introducing a reference count. Okay, so to track the usage, whether there is still live pointers to a kernel object. And if there is a live reference to the kernel object, then we try not to free it and try not to, again, double free it. But unfortunately, because these reference counters are not like smart pointers automatically increased or decreased by the compilers, okay? So they still is managed by developers, and when developers make a mistake, then we can still have these memory management bugs. As we can see here, so there's still a significant portion of the bugs is caused by reference count related bugs, okay? So here is a kind of brief introduction to how a reference counter works. So we can have, again, reference, which are pointers. And whenever you have a new pointer to the object, then we try to increase the reference count. And whenever a reference or pointer to an object is released, for example, is replaced by another object or set to none, then we basically remove that reference count. Okay. And when the reference count reaches to 0, we think there is no basically live reference to the object, then we can safely basically free that object. But again, because this is all manually managed, so it's very error prone. So we can have two types of common errors for reference count. The first is fail to increase when there is a new reference, okay? And this basically will lead to, okay, dangling pointers, and if you can find the use of that dangling pointer, then you may have use of the free. And the second one is fail to decrement the counter when the reference is being removed. Okay. Previously, this can still, attackers can try to kind of introduce integer overflow on the, even for this one, so then they can lead to use of free as well. But with recent enforcement, this is integer overflow is no longer possible, but then this can still lead to memory leak. Okay, so the next is, okay, so since this is a problem, then how can we solve this problem? Okay, and there are some existing work. Some is on kernel, some is not, on basically reference counting problems. Okay, so in general, we think there are two common ways to model what is a reference count bug. Okay, well, one common strategy being used by two previous work on reference count bugs, finding reference count bugs in kernel is using this so-called path consistencies. Okay, so meaning that if you have a piece of code or basic execution passes that access the same counted memory objects, then you can track how basically they increase or decrease the reference count. If they happen to basically have different behaviors, for example, on the one execution path, they increase or decrease, and on the other path, it only increased, it doesn't decrease, then it's likely due to basically path consistencies. You can say, okay, maybe the other one is a bug. Okay, but we think this is not very good modeling because it doesn't track the, I think, the fundamental invariance we want to track, which is the reference count. Reference means to tracking references, right? So, but this technique, they are not really tracking this invariance. So they have some false negatives, as well as they cannot, for example, handle when your bug only happens on a single path, where you don't have basically one to compare with. The other work that we like is Hugi. It's basically actually tracking this invariance between reference count and the number of references. But unfortunately, it basically is only working for Python. So they leverage some of the good conventions in Python, and but they don't consider, they cannot work very well in kernel because the kernel actually have some conventions that we need to consider. So the second challenge is how do we track? Okay, so the reason is, as probably you already noticed, in order to precisely track reference count bugs, the analysis has to be path sensitive. Okay, so we need to be able to track individual paths. Then how to do path sensitive analysis on basically a huge code base is a challenge. So usually we cannot scale this kind of analysis, and so as a result, so we have to find ways to basically make it scalable. The last one is, okay, so we can leverage this strong invariance, like the reference count has to equal to the number of live references, okay? But when we apply this strong invariance to the kernel, we find out, okay, we actually have a lot of false positives. When we look into the reasons of these false positives, we find out, okay, the kernel actually have some conventions that will break this invariance, okay? So one of the most common one is so-called internal references, okay? So the kernel may create a reference, basically a pointer to that object, but this reference is not ref counted, meaning that when you create this, it does not increase the reference count, okay? So they call this kind of reference as internal reference or weak reference. And for example, there may be some caches, or basically that is used to indicate whether this kind of object exists, okay? And when you look up, then you can first look at this cache, and if you find the object, then basically increase the ref count. But this kind of reference, the reason they are not ref counted is because they only represent the means the object exists, okay? So whenever this object is freed, the destruction routine actually will automatically free this internal reference, so it doesn't need to be ref counted. Okay, so as a result, we have to basically be able to understand all these kind of conventions in the kernel in order to reduce false positives. Okay. So here basically is our kind of key observations or key ways to make build a scalable analysis to accurately track basically reference count bugs. We're using basically this strong bug oracle, meaning that we're trying to track the reference count, and we're making sure that the reference changes to ref count correspond to basically the changes in references. So they have to be consistent. But in order to make this scale, we have to basically, we reduce this analysis scope. Instead of trying to track the whole basically life scope of a kernel object, we basically divide it into smaller local scopes. So we have basically kind of four scenarios. The first is the creation, when a heap object is created, and until basically that object is stored in basically in permanent in heap. And the second is usage, where you kind of borrow the pointer and then you use it, and after that you are done. And the third one is escape, meaning that you are borrowing a pointer, but then you are going to store that pointer in another heap object. In this case, the reference count has to basically, you have a new kind of permanent reference count. And the last one is basically release, where you grab basically that reference and you try to free that object. So by narrowing the analysis scope to these four cases, then we can significantly increase the scalability of the analysis. So here's a brief overview of the workflow. So we have a static analysis trying to understand first what objects are being ref counted. Second, how the reference count is being increased or decreased with wrapper functions. Then we have basically a static analysis to basically narrow down the analysis scope. So once we have that analysis scope, then we perform under constraint symbolic execution, basically path sensitive analysis to track basically reference count changes and reference changes. So in this step, basically we're doing basically some summary-based analysis to further increase basically the scalability. And once we have this, then we can do basically bug detection. And once we find some bugs, then we basically apply some heuristics to filter out the potential false positives. I think I don't have much time, so I will just briefly go through this analysis. For more details, you can basically find in the paper. Okay. So anyway, so we implement this using basically static analysis and the under constraint symbolic execution, and we apply this to the Linux 4.14 kernel. And we can basically scale it in reasonable time. For example, the symbolic execution can finish it in about under 200 hours. It's still long, but we think it's reasonable. And lastly, basically, we are able to find 82 new bugs, including basically 31 that has already been fixed when we report it, and 52 new bugs. Okay, so as a conclusion, so we built a scalable and precise Refcount discovering tool. So we are enforcing basically strong invariance. The Refcount changes has to match the reference changes, and this tool basically integrated a lot of understand the Linux Refcount conventions, so we can significantly reduce the false positives. With that, thank you for listening, and open for questions.